Okay, so in section 9.10, we're going to work on Taylor series and Maclaurin series a little bit more in depth. It's helpful if you have some of these things memorized. There's a whole list of them in your book. It's on page 670. I've whittled it down to these four. It's just convenient to know these four. And in fact, if you know a couple of them, if you know this one, you can get this one. Keep in mind that the derivative of sine is cosine. So if you're differentiating this with respect to x, then we can ignore all this stuff because it's not a function of x and focus on this term. When you differentiate this, really what's going to happen is that this exponent is going to come out in front. So you have a 2n plus 1, and then subtract 1 from the exponent. That 2n plus 1 will cancel with one of those down here, leaving us with just 2n factorial. And if I subtract 1 from the exponent up here, I also get 2n. So if you've got one, then you can get the other one. So that's kind of a nice little trick. And if you have these things, it makes it easier to get other series. So let's start with problem number 2. They asked you for a series for f of x equals e to the negative 4x, and we want that centered at 0. Okay, e to the negative 4x centered at 0. I think we can do that. The nice thing, though, is that this is centered at 0. So is our series up here. The center of this series is 0. It's true that it has an infinite radius of convergence. You can get this to converge for any value of x. It just might take a while. Fortunately for us, the center here is 0, so that makes it really easy. Instead of an x here, I've got a negative 4x. So I'm going to put that into the series and get my new series. So my series for e to the negative 4x is going to be the sum from n equals 0 to infinity of negative 4x to the nth power over n factorial. Now, if you're really motivated, you could split this up in a couple different ways. N equals 0 to infinity of negative 1 to the n, 4 to the n, x to the n, over n factorial. It's just really window dressing at that point. These two series are equivalent. And it's nice. All we had to do was substitute into that series. Now, we did take a peek at some of this stuff last week, but let me revisit problem number 8 here, because it's kind of similar. We are going to find a series for some function of x. F of x equals e to the x. But this time we want to center at x minus, or x equals 1. So that's our center here. Now, that's going to change things a little bit, because we can no longer just, substitute in something into our known series here. And let me try and demonstrate that for you kind of graphically. So let's take a look at Desmos. And here's our last one, e to the negative 4x. And if I take our series and start adding in terms, so increasing the value of n, you can see that we're going to eventually get nice convergence to that series, or to that function e to the negative 4x. And as I add in more terms, the interval of convergence increases. But let's go down to, where is it? Where did it go? Ah, here we go. Let me shut off the previous two here, and let's go down to this one. So here's e to the x, got that series, and just to show you the series that I put up on the board works. You can see the convergence of that series as you increase the value of n. It converges pretty quickly. But what I can't do is I can't just substitute in x minus 1 in here for x, like I did here. That would certainly shift the graph, but it's not really going to give us what we need. So let me shut that off. And let's look at what happens if I plug in x minus 1. Does that work? Do I get the series that I need? Does it converge to what I want? Well, let's add in more terms, and it doesn't look like it's making me very happy. It's not equaling the graph that I have in green. So we're going to have to do something a little bit different. And the reason it doesn't work is because your coefficients change. Remember, the coefficients are going to be the coefficients that you get from a power series. And those coefficients involve the derivative of your function at various orders. So let's take a look back at that real quick. Remind ourselves of the general form of these things. So these a sub n's are going to be the value of the derivative at C, at our center. Or you can look at it over here for the definition of the Taylor and Maclaurin series. Maclaurin series, of course, is just C equals 0. But there it is. So we need to recalculate these things because the value of E, or it's going to be the value of our derivative at 1 is not just going to be 1. It's going to be something else. So let's calculate some derivatives here. Well, the general derivative of this function, the first, the second, third, the fourth, whatever, is just going to be e to the x, right? So that's not going to change. And likewise, the value of the function at c, or value of the derivative at c, is just going to be e to the first power, or e. So these coefficients have to be part of our calculation of the Taylor series. So let's put that in. It's going to be f of x, of course, is f of c plus f prime of c divided by 1 factorial times x minus c, and f double prime of c over 2 factorial times x minus c squared, and so on. I think we kind of get the general idea there. So f prime of c, or it's going to be f of c, is going to be e plus e over 1 factorial times x minus 1. And then you're going to see quite a familiar pattern, e over 2 factorial times x minus 1 squared, and so on. Now we can factor this, factor out the e here, and then write the rest of it as a summation. So let me do that one at a time. So if I factor out the e, I get 1 plus x minus 1 plus x minus 1 over 2 factorial plus x, or this should be squared, plus x minus 1 cubed over 3 factorial. So overall, my series is going to look like this. The sum from n equals 0 to infinity of x minus 1 to the n divided by n factorial. Keep in mind that 0 factorial is 1. So this should be my series for this function. I'll give you a minute to copy it down, and then we'll take a look at the graph and see how we did. Okay, so let's take a quick look at the graph here. So there's your function e to the x, and let's try looking at this graph here. Zoom back on L. So the difference is this is our series here where we've accounted for the shift and accounted for the new coefficients. If we increase the number of terms in the series, we should get more and more convergence at a wider and wider range around 1. But notice where the convergence starts. It starts right there at x equal 1. That's where the convergence starts, and then it builds from there. So the interval of convergence kind of radiates outward and increases as you increase the number of terms in this series. So nice. So the moral of the story is When you can substitute into a series without shifting a center, do so. Absolutely. Because it's a lot easier than creating a series from scratch. Now, let me demonstrate that again. And I'll put this in the notes if you want to copy it. But I'm not really going to go that slow that you're going to want to take notes. So just sit back and relax is what I'm telling you. Enjoy this. I don't tell you to do that very often. It's day before 2 days before Thanksgiving, so I want you to relax. Problem number 6. Here's problem number 6. You get f of x is 1 over 1 minus x. So what if you wanted a Taylor series for this? Well, our series is going to have a center at 2, so c equals 2. You can calculate some derivatives. It's more convenient to write it like this, so you can use the power rule rather than having to use the quotient rule. So pretty soon you see, okay, negative 3 times negative 2, that's going to be positive 6 to the negative 4. I'll write that as 3 factorial, and then you generalize from there. You get some terms like this. Then you evaluate it at 2, and again, you can see kind of a little bit of a pattern here. Nice. All right, so negative 1 to the n plus 1 times n factorial. That's the pattern here for f sub n. If you plug that into your formula for the Taylor series, you're going to get some nice simplification. Each of these terms in the numerator is going to be an n factorial. It's going to cancel with the n factorial down here in the denominator. The only thing that doesn't quite cancel is the negative signs. So, yay, okay, got to deal with the negative signs. That's fine. What I'll do here is I'll factor out the negative 1. Maybe it's just some kind of OCD thing for a mathematician that I just don't like that negative 1 out in front. All right, factor that out. I get something like this, which is a nice alternating series, powers of x minus 2 to the nth power. Yay. So there's your Taylor series. Wasn't too bad. But, like I said, if you can avoid having to create one from scratch, it's not a bad idea. So what would be a way that you could avoid creating this by scratch or from hand, from the beginning? Well, one thing you could do is realize that we've got a series for something like this, 1 over 1 minus x. The problem is we need to center at 2. So let's introduce some stuff here. If I wanted this centered at x minus 2, or centered at 2, I have to have that x minus 2 term in here. By putting that in here, minus and a minus, I've really added 2 to the denominator. So I can keep that in check or keep it in balance by subtracting 2. This is stuff that we did in section 9.8. Combine like terms. I get a negative here. So I'll factor out that negative and move it up to the numerator. In order to get the series that I need and want and know, this has to be a minus here. So instead of writing it as a plus x minus 2, I'll write it as a 1 minus negative x minus 2. Last but not least, I'll factor out that negative out in front. So what I'm left with is this right here, negative 1 times this. This is now in the form that I need for my series, so I'll take this whole term to the nth power. I've got my negative 1 out in front, and if you want, you can factor out that negative 1. Notice you get the exact same series either way. Personally, I think I'd choose the second way if I was given the choice. But both of them work. The moral of the story, though, again, is if you can use a known series to try and find these things, I'd do it. Absolutely. It's a lot more efficient. So let's do that with problem number 38. Let's use a known series here. f of x is e to the x plus e to the negative x. And that's equivalent to 2 times cosh of x. Well, again, we're going to use some known series. E to the x, we know that one. That's pretty easy. That's a sum from n equals 0 to infinity of x to the n over n factorial. Can I substitute in negative x into this series to get the series for e to the negative x? It wouldn't flip the whole thing. It would flip part of it, but the short answer is yes. You can make a substitution. If you replace x by negative x, I need to do the same thing over here in the series. So it's going to be the sum from n equals 0 to infinity of negative x to the n over n factorial. Nice. So what happens if you expand this? Well, the first few terms of this series are going to be a 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And I'm almost going to get the same thing for this series. What's the one difference in that second series? It's going to alternate. For your even powers, it's going to be positive. For your odd powers, it's going to be negative. So it's going to start out positive 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. So we want to add this up. What happens when we add this up? Well, one of two things. These terms are going to cancel, right? The odd terms are going to cancel. And the other terms are just going to double themselves, right? So let me kind of write this in a very clever way. Let's just write that that's twice 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. Nice. That wasn't so bad. And then what's left to do is to write this as a series, sum from n equals 0 to infinity. Well, let's see if we can't figure out the general pattern here. In the denominator, you're going to have an even factorial, and this is going to be matched by an even exponent. The signs don't alternate, so I don't have to worry about a negative 1 to any power. See if you can't write that down. Take a moment to see if you can't figure out, well, what would be the correct notation there? Anyone got it? X to what power? 2n over 2n factorial. This makes sense if you think about it a little bit further. The hyperbolic cosine is an even function. It's symmetric. And you're getting an even Taylor series polynomial. This only has even exponents. So this series is going to be even, much like the original function. So that's going to be equal to 2 cosh of x, which is what they asked for. But let me just point out that you can also get sum from n equals 0 to infinity of x to the 2n over 2n factorial is simply cosh of x. So we kind of get that for free, right? Just divide out the 2 on both sides. This is what they were looking for. This part right here. You know, I think that, you know, if I gave this to you, I might just ask you to find a series for cosh of x. So cosh of x would be e to the x plus e to the negative x over 2. And in your work in doing this, you'd probably rewrite this as 1/2 times e to the x plus e to the negative x, like that. And then this 1/2 would cancel with that 2 there. So you're going to get the same thing. I don't think it's a lot different, but I think this is what they're looking for in the book. Okay, good question. So let's look at problem number 10. I'm going to show you 2 ways to do this. And again, the moral of the story here is if there's a way to substitute into an existing series or manipulate an existing series to get a Taylor series, do it. Because sometimes doing this stuff by scratch is a real pain. So you can start out by copying down the function. F of x is ln of x plus 1. And we're going to try and find a Maclaurin series, which means that the center is at 0. Well, the first approach that I'm going to do is the brute force approach. I'm going to kind of breeze through this a little bit just to show you what it looks like. And then I'm going to show you the approach that I actually kind of recommend. So the first approach is a whole lot of fun. Maybe you can spend some time while you're watching the Lions lose this weekend or this Thursday, finding the derivatives of these. The first one's not too bad, but the second one requires the quotient rule. Yay, everybody's favorite. Woohoo! And the third one requires the quotient rule on steroids. And to get the fourth one, you really need some PEDs. Get that fourth one. And wow, have fun getting the fifth one, factoring it and cleaning it up. And if that's not fun enough, hey, knock yourself out and get the sixth one. Yeehaw! Wow, good times tonight. Of course, then you get to evaluate all these series at 0. The nice thing, at least, is that a lot of these are pretty easy to evaluate at 0 because that's going to disappear. That's going to disappear. In fact, all the odd terms are going to disappear. So, great. If I substitute in then to find my Taylor series, then I get something like this. And down here at the last, I didn't feel like thinking about it too much, so I wrote it. 240 divided by 720. Oh, yeah, that's 1/3. So, overall, you get the following pattern. You got a 4 here and a 2 here, a 6 here and a 3 here, a 2 here and a 1 here. So basically, the term that you have in the denominator is half of that exponent. And that gives you this series here. So, wow. But, of course, the brutal part would be come up with these derivatives, which, no thanks. All right, so what's the clever approach? What else could we do here? The other possibility for us is to try and outwit the problem. For instance, one of the series that we derived was this. So this is going to be problem number 10, alternate method. We know we have a series for 1 over 1 minus x. If you substitute in a negative x, you'll get this series for this n equals 0 to infinity of -1 to the n x to the n. It's just like the series that we had for, in fact, let me just write it down here. 1 over 1 minus x equals a sum from n equals 0 to infinity of x to the n. That's your geometric series. Now, here's the little thing. We can note the ln of 1 plus x is really the integral of 1 over 1 plus x dx. Okay, so that's nice. Well, then what? Well, how about if we come up with a series for this based off of the series for this? In other words, I know the series for 1 plus 1 over x. That's the sum from n equals 0 to infinity of -1 to the n x to the n, and that summation has to be in here, and then I have a dx term here. This really isn't too bad. Keep in mind, this is just a polynomial, and even better, because you're integrating with respect to x, I can move that integral into here and get the sum from n equals 0 to infinity of -1 to the n of the integral of x to the n dx. Not bad. Bad. What's the value of that integral going to be? What do I get when I integrate x to the n dx? Yeah, thanks, gentlemen. So this is -1 to the n x to the n plus 1 over n plus 1. Great. That's my series for ln of 1 plus x. Almost done. Remember the original problem, though? We're trying to find a series for ln of 1 plus x squared. What do you think we need to do to finish this up then? Yeah, just replace this x by x squared. So it's going to be the sum from n equals 0 to infinity of -1 to the n x squared to the n plus 1 over n plus 1. Please be careful in working with this last little bit. That 2 has to distribute itself to both terms in the exponent. And if you're careful, we'll get the sum from n equals 1 to infinity of -1 to the n x to the 2n plus 2 over n plus 1. And that's the same that I got just a minute ago with about 3 hours worth of derivatives. What's that? Oh, actually, I went to Wolfram Alpha. I wasn't going to do that by myself. There's no way. I have a life outside of class. I really do. Trevon? What are you talking about? Thanks. Appreciate it. All right. Good question. Now, we can get away with this because substituting this in isn't shifting the center. All right, the center is still 0. So that's okay. If the center of this was going to be something different, then, wow, that'd be a whole nother mess. But we're okay on that one. Any other comments or thoughts on problem number 10 here? You know, I guess the integration might not be as clear cut if you had an x squared here, because you'd have an inverse tangent. So it would give you a different series you'd have to fuss with. Yeah. Yeah. Actually, you know what? Let's see. If you had to see, actually, yeah, you probably could do, maybe the x squared originally. I don't know. I think I like it like this. It's pretty clean. Yes, sir. Um, That's a good question. Let me think about that. Well, the constant's going to have to be 0. But why? Um, integral plus a constant. I can't give you a good reason off the top of my head why the constant has to be 0. I have to think about that one. Yeah. All right. Thank you. Let's try a couple more. Actually, let's work with a different series. So a lot of you probably heard of Pascal's Triangle. In case you haven't, it's a nice little formula to help you expand binomials in the case of integers, and you can do so by referencing the rows in this triangle. Actually, Pascal's Triangle goes back to people much, much earlier than Pascal. There's a lot of cool things in Pascal's Triangle, like the triangular numbers are part of one of the rows there. You can see it as the third row down from the side. You've got your triangular numbers, your tetrahedral numbers, etc. There's a ton of stuff. Fibonacci numbers are in there as well. But I want to get down to Newton's contribution. Newton realized that this formula is actually good for something other than just integer powers. That this actually forms an infinite series which converges for values of x between 1 and -1. So we're going to take advantage of that and try and find the couple series, starting with problem number 18. Let's ditch this back here. Did you guys copy that down at the beginning, the very, very beginning? It should be in your notes from that first little set of 4 series that I gave you. Or do I need to write it down again? It's in your book, page 670. You need to reference it there. Problem number 18. We have f of x is 1 over 1 plus x cubed. So we could also think of that as 1 plus x to the -3rd power. And that -3 is your value for k. So if you're looking at k from the binomial formula, 1 plus x to the k power, that's it. So how does this formula work again? Well, let's take a look back at it. And really all we have to do is substitute in for k. Unfortunately, these things don't have a nice, easy pattern that you can summarize with a nice summation, at least not that I'm familiar with. So it's going to be a 1 plus k times x, and then plus k times k minus 1 over 2, and so on. And this is going to be a factorial term, and you're going to keep on multiplying by an ever-increasing product. So back over here, that's going to equal 1 plus -3 times x. So there's your -3 over 1 factorial plus -3, and then when I subtract 1, I get -4 x squared. And the series continues. So -3, -4, and then -5. This time, what am I going to divide by? 3 factorial, x cubed, and so on. Okay, so last one, -3, -4, -5, -6, and so on. Now the radius of convergence for this one is 1. I think this will simplify to 1 minus 3x plus 6x squared minus 15x cubed plus 21x to the 4th. You can actually, in this particular case, I think it's maybe because this is a nice integer, you can summarize this with a series. It's not always easy or possible to do. But these numbers are actually numbers that you would see in Pascal's triangle. If you look back on the video or look up Pascal's triangle, these are your so-called triangular numbers. No, are those the triangular numbers? No, maybe not. Tetrahedral numbers? Maybe. Yeah, one of them. Got myself curious here. Let me look back. Let's see. There we go. No. So 1, 3, 6. Yeah, they are. Missing the 10 though. 15, 21. 6. Oh, you know what? There's a mistake in my. Oh, okay. So they are the triangle numbers. I just had a mistake here. Let's look back here. That would be -60 divided by 6, which would be 10. So that'd be a 10, and then this would be the 15. So, my bad. In any case, we can actually summarize these things as n plus 1 times n plus 2 over 2 times x to the n. Now this gets a little bit more involved if you have a non-integer exponent, but it's still doable. I'm not, in the case of problem number 24, which we're going to do next, ask you to write it in this form. You might be able to write it in that form, but it's got to be a real challenge. So, are we okay with problem number 18 here, though? Donnie? Okay. Let's take a look at problem number 24. F of x in this case is the 4th root of 1 plus x. If you're going to apply the binomial theorem, we need to rewrite this as 1 plus x to what power? Good, 1 plus x to the 1/4 power. So again, the nice thing about that is it tells me k. K is equal to 1/4. All right, so let's take a look at this. That's going to be 1 plus k, which is 1/4, times x plus 1/4. And what's 1 minus 1/4 minus 1? -3/4 over 2 factorial times x squared. And this gets a little bit more fun here. 1/4, -3/4. What's going to be the next one? Yeah, you're right. -7/4 x cubed And let me see if I can't squeeze in one more here. 1/4, -3/4, -7/4. Someone else other than Slav for the next one. Ronnie, what's the next one? -11/4. Cool. We can clean this up a little bit. It doesn't clean up a lot. 1 plus 1/4 x, and then minus, I'll have 1 times 3 over 4 squared times 2 factorial times x squared plus, let's see, trying to decide if I want to clean this up a little bit. That's going to be 1 times 3 times 7, or 3 times 7 is 21. 21 over 6, you're going to get some cancellation. The 3's will cancel. So 7 over 128. So 7 over 128. X cubed. And the last one, what a monster that one's going to be. All right, so you're going to have a 4 to the 4th power from all these. So that's a 4 to the 4th times 4 factorial. And then 3 times 7 times 11. X to the 4th. Let's see if we can't simplify that on our graphing calculator. So it's going to be 21 times 11 divided by 4 to the 4th times 24. And wow, lovely garden variety fraction of 77 over 2048. That'd be 32. X squared minus plus 7 over 128. X cubed minus 77 over 2048. X to the 4th power plus dot 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 dot. Tell you what, on the final exam, I'll only make you go out to 8 or 10 places, okay? Yeah, only 4 problems like that. All right, let's take a kind of a quick look at this and see that it matches a little bit of our expectations. Let me shut this one off. And yeah, I think this is the one we want here. No, I got to get rid of one more function up here. Goodbye to e to the x. And let's turn this one on. So the 4th root. Probably want to change the window size. Maximum of 1.5. That should do it. Okay, so let's take a look at the first 2 terms. First 2 terms, you're just going to get a straight line as tangents to our function. Okay, not bad. Keep in mind that the center of this is at 0, so your approximation is going to get better and better starting in an interval around 0. Let's just one try the squared. Not bad. Getting better with the cubic function. Shut these off and go to the 4th power. And overall, getting pretty good. Remember, this is supposed to be a good approximation on the interval -1 to 1. And we're doing a pretty good job with just 4 terms there. So that's not too bad. Okay. Comments or thoughts on problem number 24? Let's look at one last problem like this. It's going to be problem number 20. Some of these notes that I've kind of flashed up and said, oh, here, let's just look at this. I'll include those in the notes that I scan and put online. Going back to problem number 20. I want a series for f of x equals 1 over the square root of 1 minus x squared, which of course this is 1 minus x squared to the minus 1/2. Does anyone see a problem that we're going to run into here trying to find a series for this? What's different about this one as opposed to the last couple terms, last couple problems? All right, that's negative. All right, so that's one thing. What else? What's that? K is negative, that's okay. That doesn't hurt. There is one other thing that's different about this. Fine? Yeah, this is squared. So there's a couple things that we're going to have to take care of. And what I suggest is maybe we take care of them kind of slowly, one at a time. Let's first derive a series for what I'll call g of x. And g of x is going to be 1 plus x to the minus 1/2. So eventually my goal is twofold. First of all, I'll get a series for this. Then I'll create a series for h of x equal 1 minus x to the minus 1/2. And then once I have that one, then I can substitute in x squared and get my series for x, or for f of x. So that's the game plan on this one. We okay with that? That way we don't have to derive it from scratch. Basically, you can just use the binomial formula that we're given. All right, so let's take a look here at g of x. So as before, we'll start out, that's k. So g of x is going to be 1, and then k times x plus negative 1/2 times something over 2 factorial times x squared. What's that something going to be here? What's the negative 3/2? Thank you. Plus negative 1/2 times negative 3/2 times negative 5/2 over 3 factorial times x cubed. And so on. If we clean this up a little bit, it's going to be 1 minus 1/2 x plus 1 over 2 squared times 3 over 2 factorial x squared minus 1 over 2 cubed 3 times 5 over 3 factorial times x cubed. And I'm not trying to really clean it up too much because there certainly is some cancellation I can get here, but I'm trying to write it in a way that I can kind of see the pattern and write the next terms down if I need to. It's going from plus to minus to plus to minus, etc. So the next term is plus. It'd be 1 over 2 to the 4th power, 3 times 5 times 7 over 4 factorial times x to the 4th. And so on from there. So that's the first step, and that was the hardest part. The rest of it is going to be making a couple quick substitutions. Are you comfortable with our series for g of x? The nice thing is that the next two are really just substitutions. What do I have to substitute to get the series for h of x? Using my series for g of x, what do I have to substitute to get the series for h of x? Yeah, negative x. H of x equals g of negative x. So I'm going to plug in a negative x here. Can we think that one through? What's the negative x going to do? What kind of terms are going to be changed by the negative x? Are the even terms going to be changed? If I put in negative x and square it, is that going to change anything? What about the odd terms? So what's going to happen to the odd terms? They're going to turn positive. So that's not too bad. 1 plus 1/2 x plus 1 over 2 squared, 3 over 2 factorial. Basically, I'm going to take all these terms and make them positive. Almost done, right? I've got h of x. What's the last thing I need to do to get f of x? Not quite multiply them together. It's not a square root. What's the difference between h of x and f of x? So I got an x here and I got an x squared here. So to get from here to here, all I have to do is take h of x and substitute in an x squared. So h of x, or h of x squared, is going to be my f of x. So it's going to be 1 plus 1/2 x squared plus 1 over 2 squared, 3 over 2 factorial, x squared squared again will be x to the 4th, and so on. What will I have here? X to what power? 6, thank you. I was holding my breath. I hope somebody wasn't going to say 5. I get that from my algebra students. Yeah. All right. Glad I don't get it here. X to the 8th. Cool. Let's do one last one, which I'm hoping is going to be pretty quick. Before I do that, are we okay with what we did here? We kind of rewrote this a couple different times. We started out with a series that fits the binomial series. We substituted in negative x, got a series for that. And then substituted in x squared, got a series for that. So, you know, in hindsight, we probably could have maybe just done that in one step. That's okay. Yes, sir.
Are you going to tell us how many terms we're going to go to?
Yeah, I'll tell you how many terms that I want. But four-ish is probably the most I would want. I don't want you spending too much time on this. All right, let's send you off with an easier one. Problem number 36. G of x is 2 times the sine of x cubed. What would you do with this? If we're trying to find a series for that one, how would you approach it? Yeah, use the sign summation formula, right? So the problem says find the Maclaurin series for the function. Use the table of power series for elementary functions on page 670. So we've got a formula for this series. Sine of x is the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So one thing I can do is realize I need twice some series. So it's going to be twice of something. See if you can't figure out the rest of it. What are you going to do? So what are we going to do? What'd you do on yours? Anyone? Come on, make me look good. Let's go down on the World Wide Web. Yeah, sub in the x cubed, right? We've got a series for sine of x. You're not changing the center of that series, so yeah, just sub in the x cubed. So it's going to be x cubed instead of x. And that exponent is going to multiply. We'll get twice the summation from n equals 0 to infinity of negative 1 to the n, x to the 6n plus 3 over 2n plus 1 factorial. That's it. There's your answer. Yeah, the whole test will be that one. And afterwards you can come up and hit the button.
That was easy.
Yes. I think I have that one programmed in. Let me take a quick look. Let's see, 36. Yes, good for me. So let's shut off the previous one. So that's this one. And this one's a nice series. So here's the actual graph. Let me zoom out a little bit. And let's start out at m equals 0. As you add more terms, what should happen is that our function in orange should start to converge to the function in green over a wider and wider radius. So let's see that happens. There we go. And you can see that the interval of convergence is expanding. So it's kind of nice. Actually, let's automate that. All right, there you go. So in and then back out. All right, I think you get the idea. Okay. For homework, try 1 through 9, 17 through 37, 55, and a bonus one, 58, which isn't in the answer key, but I like you to work on it anyways. All right, good luck.